Okay, so a little reminder as usual. We study the Yangian. Yangian. It is defined in the RTT presentation using the R matrix by this relation. More precisely, the generators are, this is my notation, and I recall the indices are satisfy this convention, and M, the superscript, is equal to, with the understanding that is the Kronecker delta, and then the defining relations. Relations can be written as follows, in more detailed form. The commutation relations. I'm sorry, these are not strictly speaking commutation relations, but just the defining relations. And here I assume that M and L takes the values starting from 0. And one can prove that the true commutation relations, which are equivalent to this system, are as follows. The sum over R from 0 to minimum from M and L minus 1 sorry. Okay. For instance, to better understand the structure of these formulas, for instance, we have the following relations. This is one sum, one combination next to this one, And remark that these terms are Kronecker deltas. So this is, and this is, I'm sorry. Okay. Okay, now I want to introduce the filtration. One filtration I already introduced before. So there are two filtrations, two algebra filtrations in the Yangian. The first it is defined by proclaiming the degree of a generators. The first type degree of the generator is by definition equal to m. This is first version. And the second version is as follows. And let's see why it's reasonable. So what does this mean? This means that in the first filtration, this is my definition for the first filtration, and the term of degree less or equal to m, given some natural number m, is by definition the span of the monomials in the generators, some finite number of terms, subject to the restriction that the sum of the superscripts is less or equal to m. So this is the definition of the first filtration. But for the second filtration, the definition is different. It's again the span of the same type, but instead we have this condition. Okay. So we know what we know. We know that the associated graded algebra with respect to the first filtration is a commutative algebra. Commutative algebra. Actually, this is the algebra of polynomials in countably many generators. The algebra of polynomials in countably many generators. Let's denote them as follows. This is the highest degree term of our generator of a Yangian, which means that we regard our generator modulo the filtration term of degree m minus 1. So this is my notation. My notation will be as follows. Denote is as follows. This is the element of a associated graded algebra, and denote it the highest degree term. With respect to the first filtration. But what happens? What about the associated graded algebra with respect to the second filtration? So here we have a commutative algebra, but this algebra is already non-commutative. And we have the following proposition. The second version of the associated graded algebra is isomorphic in a very natural way with the universal enveloping algebra of a GLN tensored with the algebra of polynomials. So this is the claim. Let me explain a little bit what this means. More generally, some comment. Assume that A is some algebra, arbitrary, associative algebra over the field of complex numbers. Then we can form the algebra of matrices with values in A, which is the same as the tensor product of two algebras. One is the algebra of matrices, and the other is our algebra A. So this is also associative algebra, and then we can transform it into a Lie algebra by taking as the bracket the commutator. So we get Lie algebra, the same vector space, but with the bracket, it's a Lie algebra. Let's denote it. Denote it as GL and A. And in this notation, one can say the G. Maybe I will write, I'm sorry, I will change this notation a little bit. I will write as follows. So this is precisely GL, and with the values in the algebra of polynomials in one variable. So this is the claim. This is the claim. We form this Lie algebra. We take the universal enveloping algebra, and the claim is that this is the second graded algebra. How to see this? We have a natural basis. Natural basis in this object, in this Lie algebra, is formed by the matrix units and times the monomials. So these are usual restrictions, and M is a non-negative integer. And we have the following commutation relations, which follow from the very definition of our algebra. to one basis, it's the other. And the result is the same formula as usual, but only we have these terms. So this is quite evident, I hope. Some questions, maybe? Okay. So this object, this algebra, is generated by the very definition of a universal enveloping algebra by these symbols, of such symbols, with the commutation relations of this form. So it's an infinite dimensional Lie algebra, and, but there is no problem to form the universal enveloping algebra. So now we want to prove why we have this identification. The idea is follows. We want to understand how to interpret. So proof of the theorem. So we want to understand what is the highest degree term with respect to the second filtration. What is this? So we need to understand what happens with our commutation relations. And what are the commutation relations? I mean this one. These commutation relations. What happens with this formula when we pass to the associated graded algebra? So the idea is that we have to neglect the lower degree terms in this formula. So what is the idea? We have to understand what is the degree. The degree of this term is m minus 1 and L minus 1. So the total degree is equal total degree is m plus L minus 2. And what we have here, and here you have, and on the right, so let me write more. On the left-hand side of the is equal to m plus L minus 2. And what happens with this term? Look at this. I'm sorry. Here the degree, the degree is m plus L minus 3 in general. But there is some exception. There is some exception because if R is equal to 0, if R is equal to 0, then this is a constant, and the degree is only m plus L minus 2. Okay, so, and the same happens if this index. No, it's okay. So the conclusion is as follows. So the right-hand side has the same degree, due to terms with r equal to 0. And other terms have smaller degree. This one. So keeping the highest degree, we exactly get this type of commutation relations, which comes with deltas. These deltas just come from these terms. So this is essentially the proof. So the key idea is to associate to the generator element it's not a rigorous proof, because we also have to check that the obtained elements. So one can say that this corresponds to modulo elements of lower degree, which is equal to the degree of this element is equal to m minus 1. So we neglect the terms of degree m minus 2 and smaller. Is it clear, this argument, or not? Please ask if there are some questions. Is it okay? Of course, we have what we did exactly. We have constructed an algebra morphism, which is surjective morphism from our universal Lie algebra to this graded algebra. We need to prove that the kernel is trivial, but this is the consequence of the Poincaré-Berghoff-Vitti theorem. Little argument will show. So keep this claim. Next, I need one more result, which is a curious claim as follows. So assume A is a Lie algebra of finite dimension. And assume that the center of a Lie algebra is trivial. So this is the center of a Lie algebra is trivial. Now the claim.
Grigory Iosifovich,
Да.
I'm sorry. How is the last claim related to Poincare-Bergov theorem? So why exactly is the kernel of the map is 0? It seems to me that Poincare-Bergov is related to the first filtration more.
I need the Poincare-Bergov theorem for the Yangian. It says that there is a basis of the Yangian which consists of ordered monomials. Okay, we can choose some linear order on the generators, and then we know by the Poincare-Bergov fit for the Yangian that the ordered monomials are linearly independent. And on the left, we also can form similar monomials from the Poincare-Bergov fit, this time for the universal envelope algebra.
So the claim follows just from the fact that this map is surjective and Bergov theorem, right?
Not only surjective, but the kernel is equal to 0, I think, because this requires I think this requires some work, but I hope it's correct. I hope it's correct, because on the left and on the right, okay, I agree, maybe this needs some justification. This probably needs some justification, but I think it can be done. I'm sorry.
Okay, thank you. I think I understand it a bit more. Yes.
Mm-hmm. But anyway, this should follow from the Poincare-Bergov fit for this algebra and this algebra.
Mm-hmm.
Okay, so what is the claim? The claim is that if a center is trivial, then the center of a universal envelope algebra, not of A, but of this algebra, this is, maybe I should introduce the terminology. This object is called a current polynomial current polynomial Lie algebra or polynomial loop algebra. The algebra of polynomial functions with values in our Lie algebra. So we claim this, that the center is also trivial. This is not evident at all, because it's not true that if the center of Lie algebra is trivial, then the same holds for the universal envelope algebra. This is evidently false. For instance, if you take A is SL2, the center is trivial, but the universal envelope algebra has a center. There is a Casimir operator. But if you add polynomial currents, the polynomial functions, it turns out that the center disappears. It's not trivial. I could not find a good proof. Proof.
А как же такое может быть? А если мы возьмем прям элемент универсально обертывающей алгебры, который был ее центр, центральный элемент какой-нибудь?
Какой?
Нет, в смысле, это центральный элемент вот А просто.
А он не будет, он не будет центральным в алгебре полиномиальных функций. Не будет. Не будет, и все.
Это очень неочевидно и контринтуитивно, честно говоря.
Сейчас, ну,
контринтуитивно?
Maybe some example of SL2 can help. For me, it's also.
Ну,
сейчас, какая там, я прошу прощения за такие вопросы, какая там структура алгебры Ли, может быть, не такая, как я думаю.
Нет, ну давайте разберемся с этим делом. Чего ж тут есть такой вопрос? Я только, значит, мне нужно только, давайте разбираться. Давайте разбираться. Давайте
Ну, значит, что наивный человек думает, что с элементами степени 0 такой элемент будет коммутировать тавтологически, а от того, что мы x в какой-то степени вешаем, ну, как КР.
Подумаю. Ну, давайте мы посмотрим. Вот, давайте посмотрим. Значит, у нас есть элементы. Давайте рассмотрим SL2, да? Значит, у нас есть E, F, H и FH. Commutation relations are I forgot precisely how to write. This is something like this. Sorry. I forgot exactly. We compute like this, okay?
Ну, по-моему, без вычислений у этого есть вполне себе, по-моему, сносное объяснение, которое говорит, что элемент центральный в исходной алгебре Ли, он в потоковой алгебре Ли будет действовать центрально в любом нильпотентном представлении. Но это совершенно не значит, что он будет действовать центрально в любом представлении. Вот. Это как бы, когда у нас есть...
Еще раз повторите, пожалуйста, что вы говорите, да.
Ну, условие центральности в исходной алгебре Ли гарантирует, что элемент будет действовать центрально в любом...
Значит, действует центрально.
Ну, в буквальном смысле, что у нас есть гомоморфизм из нашей алгебры Ли в алгебру Ли эндоморфизмов какого-то векторного пространства. Ну, И в тех представлениях, где элемент X действует нильпатентно.
Причем тут нильпатентно? Денис,
как причем? Ну, я не знаю, возможно, это мое несколько приватное представление о том, что на самом деле говорит теорема Пуанкаре, Бергофа, Вица, и о том, что такое элемент Казимира. Но если на этот вопрос смотреть с точки зрения свойственных к алгебре, то там как бы это кажущееся противоречием совершенно не является.
Ой,
нет,
а можно без коалгебрли, а просто...
Нет, это что-то...
Вот, по-моему, вот этот коммутатор, он и говорит о том, что если мы посмотрим на элемент e x в степени n, то он нам выплюнет что-то, что залезет в фильтрацию дальше, но совершенно...
Да, пожалуй, я начал немножко понимать. Не знаю, что сказал Денис, может быть, он сказал правильно. Look, what happens if when we commute with quadratic elements, no, I don't see. I'm sorry. Что-то тут не то, да. Что-то тут не то. I'm very sorry. I don't understand.
У меня 1000 извинений, но у меня супер наивный вопрос. Когда вы пишете А от X, какая там, собственно говоря, скобка имеется в виду?
Имеется в виду, что мы рассматриваем алгебру полиномов, полиномиальных функций со значениями в алгебре Ли.
Я так понимаю, скобка там, как выше писали, то есть берутся коммутаторы элементов алгебры Ли, и после этого степени у икса просто складываются.
Ну да.
Ну тогда от того, что вы e умножите на x в степени m, ну...
Да. Вот это меня и удивляет.
Так вроде бы нельзя умножить e на x в степени m. У нас как бы есть такой элемент em, и от него m в универсальное обертывающее оторвать так нельзя.
Виноват, я ничего не понял. Если я неправильно понимаю, какая скобка, но скажите конкретно, какая. Ну вот, ну хорошо, там есть такой элемент. Ну я не понял.
Идея такая, что вот есть, у нас есть... Я что-то запутался. Я действительно запутался и перестал сам понимать. Ну, в принципе, так вот, да. Вот так вот. Вот такое правило.
Ну, так казалось бы, что центральный элемент должен оставаться центральным, разве нет?
Ну, в универсально обертывающей произведение элемента алгебры Ли на переменную – это совершенно не то же самое, что элемент алгебры Ли, соответствующий элементу алгебры Ли, помноженный на переменную. Никто не вводил специально никакого соотношения, чтобы утверждать, что они равны.
Нет, ну тут надо же и так объяснять, что у нас есть.
То есть коммутировать-то они, конечно, коммутируют, но продолжат коммутировать элементы Ли со свободной переменной. Но вот
я понял, что говорит
элемент
Денис.
EX – это не то же самое, что произведение элемента E на элемент X в универсально обертывающей.
Да.
А есть у нас вообще произведение элемента e на x? То есть вроде бы...
Да. У нас будет вот что у нас будет. У нас будет, да.
То есть честного элемента x в универсальной мертвой нет, но можно представить себе оператор умножения на x, и вот он не совпадает с ассоциированным отображением, который...
Да, спасибо. Вот в чем дело, да. Извините, я засыпался на этой ерунде. Вот достаточно посмотреть вот на такую вещь. Совершенно верно. Большое спасибо. Вот так вот надо это понимать. И это не равно
Ну да, даже примерно понятно, да, когда мы будем с этим товарищем коммутировать, то там до степени икса, что ли, не сойдут. Ну, в общем...
Да, большое спасибо, извините меня, I'm very sorry. Значит, здесь мы применяем правило Лейбница. Это оно действует всегда, когда у нас есть произведение и коммутирование. Значит, мы один член коммутируем, получаем вот это, второй член коммутируем. Но это совсем не то же самое, мы не можем вынести вот этот xm, вынести за скобку. Да, это у меня был глюк. Большое спасибо, да, что вы обратили внимание. Вот в этом была засада.
А можно вот этот пример тогда выше как-нибудь посчитать, если он простой?
Посчитать. Я просто забыл вот эти коэффициенты. И там где-то 1/2, где-то 1/4, где-то с плюсом, с минусом. Вот упражнение. Как написать элемент Казимирова SL2? Я не помню наизусть. Ну, я могу это выводить, сейчас путаюсь. Но давайте не будем терять на это времени. Давайте я вам дам ссылку. So there is a reference. There is a reference. Our paper, Molev, Nazarov and myself. The proposition. Molev book. Molev's book. Proof is not difficult, but tricky. I don't want to give it. It would be nice to find some better proof, or more generally, even more generally. So the reason of this claim should be somehow related to the fact that the algebra of polynomials is infinite dimension. Somehow it should be related. So one can ask the question as follows. So assume, for instance, that we replace. So this is a problem. Not an exercise, but a problem. So a problem. I don't know the solution. So replace the algebra of polynomials by some other algebra, say commutative algebra. So take again this object. It can be equipped with the structure of a Lie algebra in the same way. Okay, and understand under which condition on this algebra A, this claim holds true again. So if our initial Lie algebra is centerless, under which condition one can conclude that the universal envelope algebra for this Lie algebra also is centerless. I don't know how. What is the solution? Okay.
Well, I could say that this is a condition under which this is like fails. So in a sense, if original algebra wasn't centerless, then the universal enveloping also has non-trivial center, if A has a circle on which it acts by 0. Like, for example, truncated polynomial algebras.
For truncated polynomials, it's not true. I think
Like,
there is a center. For truncated polynomials, there is a center. So
there is a center, yes. I say like center is preserved if you have a submodule of A on which A acts by 0.
okay, Denise, thank you very much. Maybe right.
Converse for, I think, is much harder. Like under which condition center vanishes.
Okay, but it would be interesting to have some claim of this sort. If you have some idea, or if you immediately see what happens, please write me in detail and let's discuss. Thank you. So now I come to the following result. I recall the definition of a quantum determinant. I recall it's a generating series and the definition, I recall it's the sum of the permutations, the sign of a permutation, and times such a monomial with some shifts. And we know, I have proved it, so we know it is central, which means all these elements belongs to the center of a Yangian. So I gave a proof, a little bit tricky, but nevertheless. Now we have a more precise result. So first, these elements are algebraically independent. And second, more strong, a little bit more difficult claim is that they generate the whole center. So the claim can be said as false. So actually this center is just the algebra of polynomials in these coefficients in the expansion of a quantum determinant. So this is the result. Now I want to prove it. The idea is to reduce this claim to this universal enveloping algebra. So the first step is to analyze what happens in this algebra. There is a natural splitting. Plus the SLN, and Z is the one-dimensional center. No, Z is the element which spans the one-dimensional center. And we know it's evident that this algebra is centerless. Okay. And so we can write, if you take the polynomial currents, and what we take this one-dimensional commutative trivial algebra, polynomial extension, and plus the same for SLN. And it follows that the universal enveloping algebra of this object is the same as the tensor product of this universal enveloping algebra and tensors with another universal enveloping algebra. But using this, the previous claim, we know that this is centerless. And what is the first term? And this is only simply the algebra of polynomials. Algebra of polynomials in these elements. So this is, in other terms, our algebra, our universal enveloping algebra is the tensor product of the algebra of polynomials in a single variable, this one, and this algebra which has a trivial center. Okay. So the center, so the conclusion. So the center of is isomorphic to polynomials in these elements. Okay. So this is the first step. The non-trivial part is related to the claim that there is no center here. But now we look at our Yangian from the point of view of a second filtration. Second filtration. We want to compute the highest degree term of our coefficient, the quantum determinant, with respect to the second filtration. So what is this? Now look at our initial formula. You have to look closely on this formula. So what it says us? It says us that the mth coefficient is the corresponding coefficient in the expansion of the right-hand side. So we can write that this coefficient is obtained as follows. We take the sum of the permutations Okay, we have this signal. Next, we take, I'm sorry, the second sum. I will explain what this means. And what happens? We extract some coefficients. This is the usual notation from combinatorics. If you have something. This means that we extract the coefficient, namely this one, from this formal power series, and so on. And we extract this coefficient from this power series. By the very definition. And we have to take the sum, the summation of all possibilities, such that the sum produces M. Is it clear, this point? Okay. But now we have to extract the highest degree term, and we observe that the degree with respect to our second filtration of this expression has the following form. I will write what happens if the degree is 0, then we don't need to extract 1, because degree 0, element of degree 0 is a constant, and it has degree 0 in any way, in any situation. So this explains why we have here these expressions. And if we have this condition and combine it with this expression, then we conclude that the only term of degree which should be this one may appear if and only if a single I is equal to M and all other summands are equal to 0. So this is a little argument which shows this claim. But next we also combine this with the fact that the constant term in each generating series, the constant term of is a Kronecker delta. And this means that we have to, in order to obtain some non-zero term, we need this Kronecker delta to be equal to 1. So this entails that we have for all, and hence we have actually S should be equal to identity permutation. Identity permutation. So the claim is that in order to extract the highest degree term with respect to our second filtration, the only possibility is that first, only one of these numbers is equal to m and all other numbers are equal to 0. And next, the permutation should be trivial. And all other terms produce something of smaller degree with respect to the second filtration. And it follows, it follows that the highest degree term is very simple. It is this one. So it corresponds exactly to this. And now finally, we use the evident fact. Evident fact is if you take the associated graded algebra of a Yangian, gives something in the center in the grading no, maybe one can argue a little bit different. A little bit differently. Let me say in words. If you have two central elements in the Yangian, look at their top degree terms. Okay, and they should be central in the graded algebra, and we know what is the center of a graded algebra. So we see that the top degree term is central. The top degree term can be produced by the, how to say exactly. So take a central element of Yangian, look at the top degree term, compare it should give central element of so it is a polynomial in these elements. Next replace each by and take the corresponding polynomials and compare and subtract these polynomials in these elements which are already our coefficients, and we get a central element of smaller degree, and by induction we get our claim. Is it clear or not? I'm sorry for...
Not very much like more geometric explanation, but formulas seem pretty convincing.
Я не понял, Денис, повторите еще.
Я бы хотел немного более геометрическое, конечно, объяснение этого, но формулы выглядят убедительно.
Ну, геометрическое, не знаю. Ну, хорошо. В общем, короче говоря...
Извините, а я не понял, что утверждается, что...
То никакого других центральных элементов, кроме коэффициентов квантового определителя, больше нет. Что они порождают все. Еще раз, давайте я еще раз скажу по-русски, мой английский, конечно, очень плохо в такого рода объяснениях. Еще раз, берем какой-то центральный элемент, смотрим на его старшую компоненту. Так и подбираем такой полином от наших коэффициентов d, который совпадал бы с этой компонентой. Это мы можем сделать, поскольку мы знаем, что это старшая компонента, нам дает центральный элемент в универсальной обертывающей алгебре. А центр ее мы знаем что ее центр есть свободная алгебра, свободная коммутативная алгебра, порожденная вот этими элементами. Они соответствуют вот этим элементам, нашим коэффициентам. Поэтому мы можем подобрать такой полином от наших вот этих уже любимых элементов, который будет иметь ту же самую старшую компоненту. Значит, мы вычтем и сведем дело к центральному элементу меньшей степени. И так
Сейчас, а это очевидно, что после вычитания центральный элемент получится?
Ну, а как же, если мы взяли один центральный элемент и вычли другой центральный элемент, то все, все будет хорошо. Так что, это такое как бы такое рассуждение, что типичное такое рассуждение, что многие факты можно сводить из фильтрованной алгебры к градуированной алгебре. В этом, так сказать, и состоит польза. Когда мы переходим от фильтрованной алгебры к градуированной, какие-то вещи упрощаются. Yangian сложная штука, а когда мы берем присоединенную градуированную алгебру, мы получаем нечто попроще. В случае одной фильтрации мы получаем просто вообще коммутативную алгебру. Это полезно в какой-то ситуации. А в этой ситуации эта первая фильтрация, она не работает, потому что мы центр так не ловим. У нас все становится коммутативным, и это нам ничего особенного не дает. Если мы возьмем другую фильтрацию, которая нам улавливает нечто иное, мы уже получаем некоммутативную алгебру, эту алгебру полиномиальных токов. Ее центр оказывается очень простой и ровно такой, какой нужно. То есть с точки зрения центров, вот эти две алгебры, наш Yangian и универсальная обертывающая вот эта вот алгебра, их центры, по сути, одни и те же. Как бы. Вот на этом идет игра. Ну, кое-как, значит, я выплыл с этим. Есть ли какие-то еще вопросы по этому делу? Ну, хорошо. Окей. Let me discuss now the coproduct, co-multiplication. So what is co-multiplication? Why is it interesting? So assume first we have some semigroup. Maybe I want to say a finite semigroup. Finite semigroup, some preliminaries. Take the semigroup algebra, which is a formal sum of these one-dimensional subspaces. And they claim it is a bi-algebra. What this means? This means that we have the usual product, multiplication, and we have another map, delta, which is very simple. Given element gamma, we assign to it the element on the diagonal. And this gives us two maps. One map is multiplication. The usual structure, the usual product in the group, in the semigroup algebra. And another is a linear map, and because this is very simple, because this semigroup morphism, this is a semigroup morphism, it extends in a natural way to the semigroup algebra, and the semigroup algebra of this object is the tensor product of this one. And the main claim, so this is the multiplication, this is a co-multiplication or co-product. There are some natural axioms relating to these two operations, and the key axiom is that this map is a morphism of algebra. So the co-product should be consistent, compatible with the algebra, structure. This map should be an algebra morphism. And this is quite evident. Assume next that gamma has a unit, and this produces us two maps. One is this one, quite trivial, and the other is the so-called co-unit. Co-unit is, which is as follows. Equal to 0 if gamma is distinct from the unity, and 1 if gamma is the unity. So there are some little extra structure. The unity map, this one, and the co-unit, this one. And again, some natural axioms which express the fact that we have a bialgebra. And finally, if G is not only a semigroup, if gamma is a group, so gamma finite group, the extra structure is related to the extra structure. Structure is related to the inversion map. It is expressed in terms of a group algebra by the so-called antipode map. Antipode map. The antipode, which is an anti-automorphism. Anti-automorphism. Again, there are some natural axioms which relates the antipode with the co-unit. This is a little bit boring. It can be viewed anywhere where it's explained what is. And this structure is this collection of operations: unit, co-unit, product, coproduct, and the antipode is called the Hopf algebra. Hopf algebra. So the model, the simplest model example of a Hopf algebra is the group algebra of a finite group. But in this case, in general, the multiplication can be not commutative, but the co-product is commutative. And so in this case, the group, the finite group case, we have the square of antipode is the identity map. And the co-product is commutative, co-commutative, which means that it is a map. So in general, if you have some Hopf algebra, we have the co-product is this map. And co-commutativity means that our delta coincides with its image, which is obtained after swapping these two factors. But in this case, we have evidently commutativity. But now I want to introduce the Hopf algebra structure. Hopf algebra structure in a Yangian, which is not co-commutative, and the square of the antipode is not identity. Let me at least start the definition. So what we need to introduce the coproduct. Coproduct. What is this? The definition is as follows. If you want to apply to our generating series, then this gives us the following. One can say in the Hopf algebra terminology, this means that such an element is group-like. more
It's-
precisely. Some question, please ask.
I'm sorry, I think group-like element is some factorized expression.
I'm sorry. Yes. I'm sorry. You are right. You are right. You are completely right.
One can say that this is deformation of a group-like element, but
Actually, this element is group-like. I'm sorry. This is not
yes.
group-like. Excuse me. Excuse me. So forget about this. This is the definition, or more precisely, this can be written as follows if you want. So what is the double sum? Okay. So this is the definition. Now we need to, what we need to verify, the main axiom, the main axiom to verify that it's compatible with algebra structure. The algebra structure. So we have a linear map. This extends because this, we have to prove that this extends to a linear map which preserves the multiplication. How to do this? One idea is to just to go to the very beginning. I mean, these defining relations, and try to verify that they are preserved. But there is an easier way to do this, namely to manipulate with the RTT presentation. So let me explain how to do this. The idea is as follows. To write the definition, first we have to write the definition of the coproduct in the matrix notation. In the matrix notation, we have what does this mean? So I assume that, so what is, this is an element of what? Let me write it as follows. Here V is our vector space. And this is by definition my Yangian tensor with formal power series. So we can assume in general that we take some number of copies of our Yangian's tensor product and some number of copies more generally. We can deal with such guys. which are parameterized by indices 1, 2, 3, m, and this is a different notation for the copies of the Yangians. So this notation corresponds to this picture where L is equal to 2 and M is equal to 1. And this is the definition. The same definition as the initial one. Okay? And now the idea is just to prove the following. The fact that our definition is consistent with the algebra structure is equivalent to the following relation. There is no square bracket here because this corresponds to 2 copies of NV. Now we take and we should prove that this is the same as and how to do this? The key idea is the following. The key idea, I have to stop just now. I would like only indicate the idea that this object and this object are permutable. This is related to the fact that the indices are disjoint. And using this and applying the RTT relation, one can easily prove this. I will do this computation in more detailed form in the next lecture. I would like only to indicate the idea. And very simple, actually, very simple. Okay, let me stop at this moment.